in technology, either in terms of device or materials getting. So based on that we'll discuss. Then what are the initiatives by the Indian government, the future plan, what are the areas where students, researchers, professors that they can focus in this field to grow their career. We'll discuss the opportunity of the semiconductor field, because all of you know India right now is the right place to enter your career in semiconductor, or you can say in VLSI. So VLSI is a large scale integrated circuit. That circuit is a big demand because most of the circuit chip we are purchasing from other country like Taiwan, Korea, China, but our Prime Minister Modi initiated lot of initiative. In last year, I think all of you heard, almost 173,000 crore fund given basically to set up the semiconductor field, semiconductor industry. And so many semiconductor industries started, 3 in Gujarat, 1 in Assam, 1 in Odisha. So that one also we'll see. How you can enter in VLSI, that one also we'll see. Okay. So first, in small introductions, like semiconductor are the backbone of the modern electronics. I already spoke, like without semiconductor, we cannot imagine integrated chip. Without integrated chip, you cannot imagine electronics device. We can imagine, but right now, we want the device to be smallest size wise low, power dissipation should be less, it should be reliable, getting lot of parameters there, its size should be very less. So based on that, we have to do lot of work in semiconductor, first in the material level, then device level, then we can go for circuit level. Getting. So we have a rapid demand for higher performance, smaller size and energy efficient. Like if you are thinking a laptop, if it consumes like more power, then no one will purchase laptop. Always when you are going to purchase any mobiles in shop, first of all what we are checking, how much battery backup, how many days, what is the size, memory, device size, like mobile size, what are the features. So that means we have to check first. So it should be small, portable, getting not only mobiles, even in agriculture field, like pacemaker, pedometer, getting every device, it should be portable. If device is very small, if you are thinking like pacemaker, that is in your body have to fix. Okay, to save people's heart attack, getting. So for that, you can imagine how much size. If you are thinking complete pacemaker, getting inside pacemaker, lot of things, processor also should be there, memory also should be there, because without memory, it should not store. Without storing your program, your processor will not work. Getting. So that device should be small, efficient, battery backup should be also very good. Getting. Otherwise, today you said your pacemaker inside your body, after 5 days again you cannot change. Getting a point. So a lot of things are actually researchers working on this. I have also published 2 papers, that is a memory for pacemaker. Getting. For IoT applications. IoT also. We'll discuss that. So that is the requirement day by day. Okay, for sustain our life, for sustain electronic device, to sustain electronic gadget, getting. So we have to lot of work. And so we'll start from transition from traditional CMOS scaling to new material. So all of you know, like the traditional CMOS Even we'll discuss some device by using traditional MOSFET. Okay. So first of all, it was like in 2010 or 1999. That time technology was like 3 nanometer, then 1 nanometer technology, then 360, again 90, then 60, 45, like that scaling. So if you scale, but if I reduce the 6 size, means just think in different way. Person. So if you will reduce the person size, sometimes what happens? Characteristics will change. Means it will not work. Like same device, it will get in. So beyond that, we cannot reduce, because that first, like that device or a circuit is designed by device like MOS, NMOS, PMOS. Getting. So that circuit you design by NMOS, PMOS. So you have to reduce the NMOS, PMOS size. Then you can design big circuit. But up to certain level, like up to 22 nanometers, in NMOS, PMOS, no problem. If you reduce further, then what will happen? Channel length, like short channel length, lot of problem will happen. Get it? We'll see later on. Okay, so then we have to design different devices. Even by using simple materials, if not possible to design, then we have to think different materials. Get it? So researchers working in different area, like someone in material engineer, material science, someone in device level, like NMOS, PMOS, getting CNFAT, FinFAT, getting then memristor, MPG, different device. Okay, by using different device, then we'll go for circuit. Okay, but our basic goal is to design the smallest device. Its performance should be very good, so that next level will go for circuit level. So big circuit you can design by using large number of devices. If circuit will be bulky, it makes it more like data. If you are talking like memory, more data you can store. Get it? So we'll come to the point. So then next we'll see about 3D architectures and AI driven design also. Get it? So our goal is to advance in semiconductor manufacturing, and this is possible by using innovations, and this innovation will set in tomorrow's chip. You have to do the innovations either in material level, either in device level, either in circuit level. Then your chip will be safe. Otherwise, I already told 10 years back, if any chip is there, that chip right now is not good. Like microprocessor, if you are thinking, Pentium board processor, how many nowadays people using? No one, because it is very slow. Getting a point? Is it clear? If 20 years back mobile if you are using, right now it is slow, it is useless, because memory is not up to that level. Getting? So what we have to do? We have to explore breakthrough materials. So we have to work on materials. We have to design novel architectures. Getting? Then AI driven fabrications we have to use, which is powering the next generation of the semiconductor technology. Getting? Now, driving innovations in a semiconductor technology. Basically, here you can see semiconductor power modern electronics like smartphone, computer, lot of things I thought already discussed same things. So industry demand high performance, smaller size, and improved energy efficiency. Getting? Why industry required? Because industry also depends on users. If you not purchase, I think just think about Nokia. Up to 2000, all of people said they were purchasing like Nokia mobiles. After 2000, I think 2000, correct sir? After 2000, other mobiles came like smart mobiles. Why they are not purchasing Nokia? Because Nokia failure to upgrade their technology. So industry have to update, otherwise you will be the People will not like, people will not purchase your device. Getting in industry also there is a competition. Each of industry they are trying to find the best technology, best facility, best device, best getting so that if they the first time all facility whatever required user, then you will purchase, then that industry will grow. Because our goal, our people also always thinking the device should be small, it's long duration portable, it consumes less energy, okay, reliable, okay. So lot of times based on your requirement, actually industry have to design. And how industry can design? There also depends on their engineers, on researchers. So in researchers, engineers have to innovate either materials, device or circuit or AI driven based getting. So finally shifting towards new materials, I already told, new device, new architectures and AI driven automations. Okay. These advancements aim to sustain Moore's law and meet evolving technology needs. I think all of you know the Moore's law because Moore's law told in each 2 years the device count per chip will be twice getting. So why we are doing, why actually that is happening? Because we are reducing the device size getting. So in same diagram, same chips, number of same example I told in this class. If you reduce the seat place, then more seat we can share side. If you reduce, then more chair you can sit in this one. Getting my point? Now technology will think in different way. Like is more. Anyhow we have to sit here, more faculty. Then what we do? Like one layer is fixed. Now we cannot in number of seat. Because if you reduce the seat size, then faculty cannot sit. Getting my point? Then what we have to do? Multi-layer, like one layer above that, getting other layer we have to do. So that, so we'll see. Now there is actually 3D IC also coming, getting not like 2D. Earlier it was 2D, like length and width, thickness was very less, but now, okay. So that, so basically. This together this trend define the next generations of the semiconductor manufacturing. Here we'll see last 4 decades how advancing happened in semiconductor manufacturing technology. Like first 1970 to 1990, I already spoke little bit. Planar CMOS, normal CMOS. Feature size above 1 micrometer using planar CMOS 1 micrometer above 1. Getting 1 micrometer, not nanometer. Getting. Then in 2000s came strained silicon and high K dielectric base, which enables scaling down from 1 micrometer to 90 to 45 nanometers. Getting 90 to 45 nanometers. Okay, improving by reducing this. What is that technology node? Technology node means I am talking about the channel length. Technology means channel length. MOSFET channel length. So if you reduce the channel length, other character also have to reduce scaling. I think all of them know that scaling. So I am not going what is that scaling, but simply size. If you reduce, then not only one parameter. Like if you are reducing channel length, then width have to also reduce. You have to reduce the oxide thickness also. Getting? Is that clear? So it will affect on its performance parameters. Getting? Its effect on power dissipation. Effect on delay, getting its effect on area. Is that clear? So basically, as per our requirements, technology, if you are reducing, scaling, okay, then its power dissipation will be less, area will be less. So I'm not going about the device level, like otherwise one day complete it will take to study about the MOSFET only. Get it? Then 2010 onward, again researchers or engineers design new device, that is a FinFET and metal gate switch. Okay, it's technology now. So FinFET 32 to 40 nanometer. Still I am using 16 and 40 nanometer technology FinFET. Okay, I have published so many papers FinFET based memory design. Get it? By reducing this technology, not only technology reduce, if you are using this, then enhanced efficiency and integration level also. Integration level means what? Integration means device size in FinFET is very less, small size, so number of devices will be more in single chip. So integration level increase. Then in 2020, EUV lithography. What is the EUV? Extreme ultraviolet lithography. So in lithography, again I am talking in short, lithography is the step in fabrication. That is the physical design part. So once again I am repeating, basically VLSI or integrated chip is one designer working in different level. First, all of you know that VLSI design flow. So specification. So we have to specify based on that. Logic design we have to do. Logic design, then logic verification. Logically it is correct or not, like any logic equation. So logically it is correct or not, based on input output we are getting or not. So logic verification. Then we have to go for circuit design. So circuit design means schematic. Getting schematic means CMOS based, FinFET based, CNFET based. So circuit will design. Circuit level testing means circuit, after circuit design, circuit simulation have to do. Circuit simulation result find, compare with the result, existing one. Okay. And if your circuit is okay, that is called circuit verification. Then we have to go for layout design. So layout design basically is the physical design part. In VLSI industry, engineers working in different area. Someone working on like a circuit designer. Someone working on circuit design for testability. So they are testing. Okay. Someone is working on physical design. Means the layout have to design. Pre-layout simulation, then post-layout simulation. So pre-layout, post-layout simulation we have to do. If post-layout simulation also okay, then one engineer, that is not actually up to that in India happening right now also. So post-layout simulation, then engineer sending that post-layout simulated result. Okay, then if it is correct, then they will fabricate, means getting. So after fabrications again they have to check testability. If it is test okay, then actually metallization, metal content like input output, then in market it will come. Get it? So up to physical like layout designs in India we are doing. So many industries like NVIDIA, Intel, even HCL also. HCL just a service provider, means they are not hardware designing, just okay, like up to simulation level they are doing. Okay, so that is the EUV lithography and GA transistor. So cutting is 72 nanometers. Researchers very less working in academia in 2 nanometers load. Now it is as a research level. Okay, which achieves using extreme ultraviolet lithography and get all around transistor. That is right now in research going on. Getting it? Then recently the other chiplet integrations, modular chip designer increasing complexity and functionality at the advanced node. That one also we will see what is the chiplet integrations. Now little bit we have to see the challenging. So overcoming challenging in semiconductor manufacturing. So these are the first one is the meteorization. Okay, is it visible? Okay, okay. Which limits from the quantum attack and leakage current as feature size shrinking. I already told you, if device size is reduced, like in MOSFET also, then a lot of problem will happen also. Like if you reduce that, then short channel effect, getting tunneling effect. Okay. Even after 22 nanometer technology, normal MOSFET, it will fail if you design memory based on that. The write everything will fail. Read you cannot do. So data storage will fail you. Get it? So that is the actually problem. Rising manufacturing cost driven by the complex equipments and advanced process. So that is also big challenge. Cost of the manufacturing. Okay. Then next is the managing thermal dissipations. In industry, basically this thermal dissipations is the big challenge, and power secured device reliability. Okay, so due to this multiple times glitches is coming in the IC. So that is also a big challenge. Supply drain constraint, limiting timely access to essential materials and components. Next challenge is increasing materials and design complexity, requiring sophisticated engineering and quality control. So these are the main 5 challenges in a semiconductor manufacturing. Here the 6 basics, key emerging technology transforming semiconductor manufacturing. What are the key? The 6. First one is the extreme ultraviolet EUV lithography. That is the emerging. That one we are going in recent year we are doing it all around. Okay. So, EUV lithography enables final patterning for advanced chip application. That is good thing. So, whatever the problems we discuss, challenging, that challenge we can solve if you are using extreme ultraviolet lithography. Second one is the like gate all around transistor. There is a different types of transistor, which represent the next evolution in transistor architecture for improved control and performance. So if you are using this, then controlling power will be improved and performance also will increase. Getting. Then next will go 3D integration circuit. So circuit level, not only 2D. We have to go for 3D circuit integration, which allow vertical stacking of component, increasing density and reducing the latency. So these are the main good things are good, or you can say the main key emerging technology. Fourth one is the chiplet and heterogeneous integration. Okay. Nowadays in industry or researchers in industry R&D working a lot of work in this chiplet. Basically, which promotes modular design by combining diverse function, block and efficiently. So that is a emerging key technology. Okay. Then fifth one. Oh, sorry. Fifth one is the gallium nitride and silicon carbide, which enhance the device performance and thermal management also. Okay, so in emerging semiconductor technology nowadays as a materials We have to choose this. Okay. Last, 36 one, AI and machine learning. AI enhancement. Okay. Which optimize the manufacturing process for yield improvement and defect reduction. So yield improvement will be there and defect reduction. Earlier what is happening in the circuit, that one will be reduced. So this technology collectively overcome current limitations and open new frontier in chip performance. Understood? Is it clear? Everyone getting? We started what is that? What are the challenges? And how we can face that challenges, how we can sort out that challenges. Is it clear? Now I am talking about the first EUL, extreme ultraviolet lithography, which advanced semiconductor scaling. Okay, so that is the advanced. Okay, EUV lithography uses 13.5 nanometers wavelength to achieve ultra fine patterning. Ultra fine patterning. I think if you are studying about that lithography process, getting CMOS process, NMOS process, PMOS process, during that pattern, etching, oxidation, ion implementation, lot of terms you heard of already. So I am talking about that. So there we are. So there also we have to improve. We have to enhance our technology. Okay. Which reduce the patterning step. So patterning step will reduce if you are using this one, EUV lithography. Compared to traditional lithography, earlier we were using traditional lithography, which enhance throughout and precision. So that is good things in this EUV lithography. So where it is happening? I am doing it or no? You are doing no. If you will be that getting, if you are doing the research at that level, then you can find. Okay? It involves high capital cost. That is good or bad? Little bit more costly means okay, but okay. Sometimes if cost or quality, if you are going in the market, same mobile, sir, I purchased this like this is a OnePlus. Its price is 30,000. Same company, same size, same color, everything, sir. Only RAM size is at this. Getting 10,000, 16,000, also 24,000. I purchased this one. Costly. But that times you have to be priority. Getting. I want more memory size because day night always lot of message, mail. We are using this mobile as a laptop. Getting all works, after the work we are doing this. So many social media. Getting. So each day, so many big video. Okay. So if you are not taking too much, so based on your work, if people are staying in village area, not using always like less data required only, then okay, no problem, you can purchase. But so based on your requirement, if you are a researcher, so when you are going to purchase laptop, first you are what actually searching configurations, what configuration you want. Based on that, why not its pricing? So based on that, why not it is high capital cost and complex source power generation technology. Source power generation technology when it is a little bit more complex. Okay, so that is one time, no problem. So designer will design, researchers will design them. Okay. Faces challenges such as mass defect, little bit in that one also. Sir, you are telling this is good, but again some research means always research. What is that? Means already search. Someone search, then that one we have to search first. We have to read. Then you can learn about that. You have to learn. Get the knowledge about that. Then you can find the problems. Problem finding is not easy. So those who are doing research. So first research review, research survey. 20, 40, 30 papers you have to read. Okay, research survey. Then research gap you can find. Then you can find the problems. After finding problems, then you should start your work. To sort out that problem. Under me, 6 students published the patent. So same way we are here. In real life, see, where is the problem? You are suffering in metro. Is there any problem? If you are sitting here, is there any problem? You find that problem first. Then solution you can find. So student, one day came in lab, I can't like see. Simply I did this project like in one lab room air monitoring system. I thought just a little bit, not directly always this one is talking it good. Little bit I'll go here and there also to make interesting like that. Okay. So he did a project like in lab, not project, was lab, one lab like a room atmosphere or air quality monitoring system. Right? Okay. So what are the different types of sensors they connected, processor and program written. It was working. So temperature control, ammonia gas control, oxygen, CO2, everything they can control. Temperature, humidity also they can control. Getting like that. Then I told that is you have basics. How you can implement this in real life? So one day he said, can I design one air quality monitoring system in Indian Railway AC coach? Yeah, why not? You can design. So what should be the novelty in that? Then he told me, sir, whatever I done, same idea will use there. But novelty is that we'll use one ozone generator. What is the ozone generator? Ozone generating. So ozone is harmful for us. But see, that one we can use as a positive. Like if you put ozone in water, then water plus ozone it will make oxygen. Getting? So inside it if you put one bucket or any tub, in that you can put the ozone, like ozone generator keep outside through pipe, you keep inside. Okay. So that when ozone will generate, then bubble will form or oxygen will. So inside this room oxygen will be more. Exhaust fan also you can keep if above this like dust particle, then exhaust from exhaust fan dust particle you can throw outside. Similarly, different sensor is there, ammonia gas sensor. So if ammonia level is more, then that ozone generator should be on. Similarly, CO2 will be more. Like that. So they design came with the idea and finally published one patent. Similarly, in research also we are doing. Okay. First we are doing the research survey, review, we are getting the problems. Getting my point? We are getting the problems. Then after getting problem, we are trying to sort out the problem. That way, day by day, technology enhancing. If you are finding mobile is a day by day, so performance is improving, qualities and more facilities. Not it is designed by one person. Thousands number of researchers or engineers are already working. Getting? Okay. So that's why here is some problem also. That's why I'm telling you faces challenges such as mass defect, impacting yield and reliability. Getting? Despite challenges, EUV is essential to sustain semiconductor scaling and cheap performance growth. Getting? So that is the So why not some problems and drawback? Okay, but overall it is a good. Okay. Now second, emerging technology, that is a gate all around, GAA. Okay. So transistor, superior control and efficiency, that is good things in this technology. In this technology, basically fully surrounded gate design using nano SiC or nano wire for superior electrostatic control. So here you can see nano wire or nano SiC. So CN also or nano technology. Okay. So see, effectively reduce the short channel effect that is happening in a normal MOSFET. Okay. Improving the device reliability and scaling. Deliver, if you are using this, so this technology deliver performance and lower power consumption compared to FinFET. First CMOS was there, then FinFET came, again better than FinFET. Okay. Its implementation in a leading edge process, Samsung 3 nanometers and PS. I am not using this on the stage. Get it? In my research, just now we are trying to work on this. Get it? So that is very emerging. Okay. And 2 nanometer nodes. That is these two companies, Samsung and TSM, using right now. Represent a significant advancement in transistor scaling and energy efficient chip design. Getting? That is a very good data. So now I am talking about the 3D integrations, like in this room. Okay, one layer is filled. Then we'll go for. So still right now, I see in your market, whatever you are using, that is a single layer chip. So now we are talking about 3D integrated circuit. 3D integrated circuit, which enhance performance and integration. 3D IC stacking vertically integrate semiconductor dia to shorten interconnect distance. So that is good thing. So interconnect distance it will short. Why? If you use like a big chip, so wire from here to here, for instance, it will be more getting. So if it will be layer by layer, then there is a wire connection will be less or short. It combines logic, memory, sensor in a compact form factor for enhanced system design. So here it will combine what are the things. First I told you memory. Those who are expert, I think sir is expert in embedded. Okay. When we are talking embedded system, means it is a processor, memory, input, output, error, getting. So that is okay. So like that, same we are in IC also here, okay, which reduce the latency, increase the bandwidth, leading to improve the overall system performance. That is good things in 3D integration circuit. It includes high bandwidth memory, that is HBM, and Intel's PORIX technology. Getting. So heterogeneous integration allow mixing different chip types and materials for modular, scalable design. Okay. Actually, one program in my college, AIT, going on, and I am the faculty coordinator there. But this is a fixed earlier, so I came here, but other faculty coordinator handling there. That is industry sponsored. There is a very big crowd. Okay. Now next, chiplet and modular design transforming semiconductor. That is the new technology. Basically, this chiplet and modular design technology divides large monolithic chips. It divides large monolithic chips into smaller, which will be reusable block connected by standardized interface. So that is a new. Modular designs improve flexibility in chip architecture and accelerate innovation. Even so many companies, even they didn't start it work on this huge industry. So whatever I am talking here, that is very emerging, latest. Okay. This breaking chip into chiplets enhance manufacturing gain and reduce production cost. The universal chiplet interconnects express, that is a UCI standard, ensures interoperability among chiplets from the multiple vendors. UCI fosters a collaborative ecosystem, enabling faster customization and innovation in semiconductor design. Now I am talking about the emerging materials. First one is the silicon carbide, SiC, which excels in a high voltage and temperature tolerance. It is ideal for power electronics. Second one is the gallium nitride, which enables high speed, energy efficient devices used in RF and power applications. Last, that is the emerging 3D materials. Ultra thin layer. In that one, basically, it's ultra thin layer with exceptional electron mobility, promising revolutionary device performance. So, electrons mobility is very good. I think you all heard about the electrons mobility in for PMOS and NMOS. So, NMOS is better than PMOS because it's the electron mobility more. Get it? Now I am talking about the AI accelerated semiconductor manufacturing. So right now, most of the researchers, industry, they are focusing AI enhanced memory, AI enhanced semiconductor manufacturing, which enables predictive maintenance to reduce the downtime and extend equipment life. That is good thing. It optimizes fabrication process for improved yield and efficiency. By using AI-driven electronics design automation, tools like Synopsys, DSO.ai and Cadence. I am using this tool. Synopsys. In Synopsys, basically H space for circuit simulation and TCAD, that is for device development. So I am using Cadence and H space instead of. It automates complex design tasks to reduce the time to market and enhance chip quality. So quality of chip will be very good. If you are using AI enhanced, then reduce time to market. So that is also very good for an industry. It manages increasing manufacturing complexity with intelligent system for better operational control.